In a region, the electric potential is given by V equal to 2x square y plus 3y square z plus 4z square x. Then the expression for the electric field, which one of the following is right? For this calculation, we are going to use that formula, that the electric field in general, that will be equal to the gradient of the potential. The negative gradient of the potential can be represented by the it is equivalent to the electric field. So this is a formula we are going to use for solving this problem. In the region, the electric potential is given by, in terms of the three variable, the electric potential should be equal to 2x square y plus 3y square z plus 4z square x. This is the electric potential. Then the expression for the electric field, they are asking what is the expression for the electric field. So already we know the one formula. When the electric field is present means if there is a gradient of the potential, suppose if you are taking the plates, here it's a positive plates, it's a negative plates, there is an electric field only exists when there is an gradient of the potential. That means the negative gradient of the potential, if it is there, then there should be a electric field. Suppose if there is no charges, then there is no electric field, there is no negative gradient of the potential. So in general, you can represent the electric field is the negative gradient of the potential. So the delta operator we know, that is equal to the I vector dou by dou x plus j vector dou by dou y plus k vector dou by dou z. This is a in general the delta operator. So the electric field, it's equal to we need to write the delta operator negative of the I vector. This is a delta operator dou by dou x plus j vector dou by dou y plus k vector dou by dou z into the vector potential, that is here, that is equal to 2x square y plus 3y square z plus 4z square x. First we need to operate one by one. Keep the I vector as it is. Dou by dou x is operating on this whole. Suppose if the dou by dou x are operating on the first term, it won't act on 2y. If it is acting on x square, it is 2x. So already 1 2 will be there, it's a 4xy. Then similarly the dou by dou x, it will, if it is acting on this term, it is 0 because there is no x variable. If it is acting on this term, it would be 4 is because dou by dou x is 1, so 4 z square. This is the x component of the electric field. Now we need to find the y component of the electric field, z component of the electric field. So the y component of the electric field, if you need, plus j vector. Now we got to operate dou by dou y. Using this one, we get to operate on these three terms. The first term is having y. If it is operating, it's a dou y by dou y, it's 1, so the remaining term 2x square. If it is operating here, it's a plus 2y, it will come, so 6y z. There is no y term here, so it would be 0. This is the jth component of the electric field. Now we need to find the kth component of the electric field. So again you got to do the same thing. Dou by dou z should operate on these three terms, so plus k vector. If dou by dou z operating on the first term, there is no z variable, it goes to 0. If it is operating on the second term, there is an z, so dou z by dou z 1, the remaining term is 3y square, plus if it is operating on the third term, it is 2z, so already 4 will be there, 8z x. So the electric field vectors, E vector in general, that should be equal to minus I vector 4xy, that common coefficient z square, minus j vector, because the front minus sign is common minus sign, you have to multiply in all terms, so j vector 2x square plus 6yz minus k vector 3y square plus 8zx. So this is the answer for this question. From the above calculation, this option C is the right answer.